Welcome to the lecture on characterization of flow. So, we talked about the stimulus response techniques. In that we talked about the pulse input and step input. So, just having an overview of that. So, as we see that if you go for the step input, then we get the F curve, and the F curve is nothing but the concentration time curve that is obtained at the outlet stream plotted on a dimensionless scale. So, then it is known as the F curve. So, you have on the y axis you have dimensionless concentration, and on the x axis you have dimensionless time. So, in the case of F curve, what we how we go with it is that at a given time t equal to 0, we are starting the adding of the tracer into the inlet stream at a rate that is maintained constant throughout the experiment. So, you have the turn days, and you are giving that tracer into the turn days constantly at a constant rate. So, that way and its concentration at the outlet will be monitored. So, at the same time we sample the exit stream continuously and plot the exit concentration of tracer as a function of time. So, we allow the tracer to go into it, it will go inside the turn disk, and it will flow as per the path which is available to it depending upon the configurations inside the vessel, and then it will coming out. And then at there we have the instrument by which we measure the concentration of the tracer at the outlet of the turn disk. So, this way the curve which we get, that is known as the F curve, and a typical F curve for the plug and mixing flow will be like this. So, that we will talk about what is that plug and mixing flow. But then you can see that your once you look at the F curve. So, this is where from here the concentration starts appearing at the exit. So, up to this much of time there is no tracer concentration being appeared at the turn disk outlet. So, the tracer which has gone inside the turn disk, it has come all through without going to the outlet, and then after that the part has started appearing at the outlet. So, it will start appearing, and then slowly it will go on increasing. So, you have a plug component, you have a mixed component. So, then mixing taking place, and then this curve is so this is your dimensionless concentration, and basically if you look at so this is 1. So, if you go for larger value, so it will go and touch nearly 1. So, that will be that will be the F curve. Now, use of the step tracer input may not be practical because of extensive contamination of the product and the cost of tracer. So, it is not very much in practice, except we can certainly go for the numerical analysis of these processes where we do not require these expensive tracers and its use. But you do not prefer that, because if the tracer is going continuously into the molten steel, so that may even contaminate the steel. So, you may like to have the concentration analysis at the exit, but then you have that will certainly contaminate the whole steel. So, that is one issue. Another issue is that since you are continuously supplying, so it also adds to the cost factor. So, the cost of tracer will be another burden. So, because of that you tried not to use it practically. You better go for the other kind of analysis like C curve or pulse input. So, we have already studied that in the C curve your injection of tracer is made as a short pulse, and resulting dimensionless, so that results into dimensionless concentration and time curve at the outer stream, and the curve which you plot for the dimensionless concentration and the dimensionless time, that is C curve, and it will rise to some value and then drop again to 0 when the entire tracer has exited the vessel. So, we already had discussed about it. Now, this is how the C curve looks like for the plug and mixed flow. So, now what happens that this is it starts appearing from here, and then it has reached to a peak value, and then further it has started decreasing, and if you increase this dimensionless time axis to larger value, slowly it will be coming towards approaching towards 0. So, this is basically the C curve. Now, that we had already seen in our earlier lecture. Now, the thing is that when we talk about these flow systems, so if you talk about the continuous flow systems, so they can be classified by the type of flow they are exhibiting. So, you have two extreme cases of possible fluid flow, and these two extreme cases are like you have plug flow and you have well mixed flow. So, they are normally considered as the ideal flow. So, in actual case you will have certainly variation from these limiting or ideal cases, and there will be non ideal cases, because in actual these plug flow, that is your ideal plug flow or ideal mixed flow, that does not exist. But so you will have the non ideal flows. They are normally present, which is practically seen inside the Tundish. Now, coming to the discussion about the plug flow. So, plug flow is so in this type of limiting type of ideal flow system, the longitudinal missing is non-existent. So, what you see that normally we define as the metal which is the tracer which has gone. So, the plug flow means the longitudinal mixing will be non-existent. So, the mixing in the longitudinal direction, that is not at all there. So, it will be maintaining its identity, and it will flow on its path. There may be some amount of transverse mixing to certain extent, in that case, in the case of plug flow. So, the necessary and sufficient condition for the plug flow system is that all fluid element have identical residence time in the vessel. So, what we see that normally you have all the fluid element which is there. So, it will go and it will exit the vessel at a time which will be same as the mean residence time inside the vessel. So, everybody has every fluid element which is flowing in that plug manner. So, it will have the same mean residence time. So, what you see here is that the flow is going and it will come and then it will be out. So, this is the example of the plug flow. So, if you talk about a plug flow system and if you talk about the C curve. So, in the C curve how can you schematically represent. So, what you see in the C curve, what you have seen that in the C curve what you do is you give the short pulse of tracer, it will go into the Tundish and then it will come, it will go inside the Tundish at a different location and then it will come through the outlet. Now, in the case of ideal plug flow system, if you talk about the C curve, what you see is that the tracer which you have added, all the fluid element will be spending a time that is equal to theta equal to 1. So, theta equal to 1 means it is the mean residence time, actual theoretical mean residence time. So, at the theoretical mean residence time, all the tracer has come out. So, you see a long peak, and then here itself it vanishes. So, all the tracer has come out of the Tundis outlet at this time, that is the time of actual theoretical mean residence time. So, this is known as the ideal plug flow, the tracer which has entered so into the vessel, and it has come and slowly it has gone and it has come out of the outlet. So, it has spent the ideal time. So, it has not interacted with with other fluids. So, either in longitudinal or in transverse manner ideally, and then it has come out and it will be, or wherever it has gone, it is basically volume by volumetric flow rate, that is your theoretical mean residence time. So, it has gone out, it has not it has maintained its identity, and then it has come out without mixing. So, that is your plug flow in the case of the pulse input system. Now, if you talk about the step input system, so that F curve, for F curve if you see the plug flow will be represented by this curve. So, where it tells that the metal, the tracer which has gone into the metal. So, this tracer has not interacted anywhere, and then when it has spent a time of the theoretical mean residence time inside the vessel, that is Tundis, then all the tracer has started exiting. So, basically tracer has been is continuously being put in, and all the tracer is flowing. So, and then it will stay together in the Tundis for the theoretical mean residence time period, and then after that they will start exiting. So, once they start exiting, then their concentration will go on increasing. So, not increasing, basically it has directly reached. So, they are all coming out. So, the concentration is dimensionless concentration is 1 itself. So, this is the representation for the plug flow, either be it when you talk it in terms of the C curve, or you talk in terms of the F curve. So, you can represent these plug flow on these two systems like these two curves. Now, next will be your mixed flow. So, the mixed flow will be the type of ideal flow that will be representing the other extreme of the mixing, that is the maximum possible mixing of the fluid inside the vessel. So, if you talk about the mixed flow, so in that case what you assume is that in the plug flow they are maintaining its identity, whereas in the mixed flow it is assumed that once the tracer has gone inside the vessel, it has completely mixed inside. So, so it is like a system, like once you have any system. So, if you have you just have an impeller, and and then you are rotating it. So, all these things will be moving like everywhere. So, this will be completely mixing into it. So, this way you will have a completely mixed flow. So, you have something flow in, and then if you have some flow out. So, so that way you will have complete mixing if you have a mixer with a stirrer or so. So, this is the example of a completely mixed flow. Now, what we know by this, if you try to analyze these mixed flow systems. So, if you see the consider the mass balance of tracer in the system, where you have put the tracer into the system. So, in that case you can write that rate of tracer input minus rate of tracer output, that will be nothing but the rate of tracer accumulation. So, what you write is that you can have the q 0 minus q c. So, that will be d by dx of V c, that is accumulation, and accordingly. So, you can from here what you can see, that if you write this q 0 minus q c. So, that will be q c, it will be the accumulation, so d by dt of V c. So, what you from here you get d c upon c. So, that will be minus of q by V, and that will be dt. So, this is q c. So, dc this side you will have dc upon c. So, this will go and minus q by V, and then that dt will go this side. So, you can integrate it, and you can integrate it by having certain boundary condition. So, if you integrate suppose, and if you are giving the boundary condition like you have you take c as q by V. So, so you have c equal to q by V at t equal to 0, and then you have c equal to c at t equal to t. So, this being the boundary condition, you can so for t you have taken the 2 time, and what will be the concentration. So, based on that you can further integrate. So, dc upon c, so it will be log c, and for the different values you will have log c upon q by V. So, that will be equal to minus q by V into dt. So, so that will be so in this case you will have so this is log c. So, that will be minus theta. So, you will have, if you look at this c value, it will be e raised to the power minus theta. So, that way you get this curve, this RTD curve for the well mixed flow. If you take the completely mixed flow, ideally mixed flow, so it will have the concentration, it will go like that. And if you take theta as 0, so initially at time 0 you will have concentration as 1, and as you move with time, so you will have the if you try to plot. So, your plot will be, so you what you see is this is an exponential decay type of curve is being seen. So, you will have this way your so this is being c and this is being theta. So, in the case of well mixed flow, ideally mixed flow, your c will be e raised to the power minus theta. So, this being 1, and your theta is increasing. So, it will be 1, this will be 1.5, and then in this way it will be increasing. So, this will be 0.5. So, you will have 0 and 0 values on the sides. So, this curve, this shows the C curve for the well mixed flow in the case of when we talk about analyzing the C curve. Now, if you try to go for analyzing the F curve. So, suppose we are talking about the step input. So, you have seen that in the case of step input for the plug flow, it has there is nothing till theta equal to 1, and then your concentration value is dimensionless concentration value is 1 altogether. Whereas, if you talk about the step input case for the well mixed flow. Now, in that case again you can have the analysis like you have the rate of tracer input and minus rate of tracer output. So, that will be rate of tracer accumulation. So, this is normally what is we have seen also in the case of the pulse input also, where we found the well mixed flow expression. So, here also this is conservation principle. So, this is rate of tracer input minus rate of tracer output, that will be rate of tracer accumulation. Now, in this case what will be happening, you will have QCI minus QC. So, that will be d by dt of Vc. So, that is your that is a conservation principle. This will lead to this value. Now, what we get? We get the parameter d theta. So, this d theta will be nothing but it will be df upon 1 minus f. So, if you try to integrate for these cases, so you will have the boundary conditions. So, if you apply the boundary condition in these cases, so boundary condition will be that you will have f equal to 0 at theta equal to 0. So, at time of 0 your f becomes 0 obviously, then your f becomes f at theta equal to theta. So, if you try to have the the integration. So, what you see is you get the integration. By integration you get f equal to 1 minus e raised to the power minus theta. So, this curve which you get, that will be giving you the f curve for the well mixed flow. So, if you draw the well mixed flow curve, so that curve will be looking 1 minus e raised to the power minus theta. So, it is nothing but 1 minus so this will be exponential curve. So, you will have if you draw the f curve for the well mixed flow. So, you will have f here and this is your theta. So, it goes like this. So, certainly this will be approaching to here it will be 1 and this will be 0.5. Similarly, you will have 0.5, 1, 1.5, like that it will be moving. So, this RTD curve that will be that will be given by this expression, it will be represented by this line. So, the thing is that what you see from this curve and the f curve which you have seen for the plug flow. Now, in the case of plug flow, what you see is that there is no increase in this tracer concentration till this point, and then here directly you have this value coming, horizontal value coming. So, what you see is that in the idealized plug flow you will have simply at this point theta is equal to 1. So, here you will have increase. Now, in this case you are seeing that it is in the well mixed flow, it is simply increasing from here. So, the thing is that as soon as it has entered, the tracer has entered, it has started mixing with the flow. So, it is idealized mixing, and that is why the pattern is like this. Now, what happens in actual case? If you talk about the actual case, the actual f curve will move like this. So, as you see that this part is basically the region which is talking about the plug flow conditions, and then you have then the mixing has started. So, ideally your mixing has, so if had it been 1 here, the theta had it been this theta as 1 here. So, ideally it has to start from here, but in actual case there is no flow which is ideally plug flow or ideally the mixed flow. So, this part will be represented by the plug region, and accordingly we will also study that you will have the plug volume also will be a component inside the vessel. So, you will have this plug component, and then you will have the mixed component. So, you have plug flow and mixed flow. Now, the thing is that when you have the plug zone and also you have the mixed zone, then what are the other zones inside the TUNDIS? So, as we have discussed, as we see that when we talk about these curves, so it will be 2 and then we go to 2.5 or so. Now, if you talk about the normal RTD curves inside the TUNDIS or in any system. So, what we see that when we talk about the the C curves where you have C and this is your theta. So, what you see that this is going, and you may go to a very large time. So, till that time the tracer is somewhat coming out or so. It means that some part it is staying very long time inside the TUNDIS. So, we have to have certain region where if the metal goes from there while coming, it takes a long time to come out of it. So, apart from this plug flow, and so plug flow will talk about the plug volume, and mixed flow will be representing later on we will be studying, that will be talking about the mixed volume inside the TUNDIS. Apart from that you will have another zone that will be dead zone. So, that zone, so normally in the vessel we try to have 3 kind of zones. So, you will have plug zone, you have mixed zone, and then apart from that, so in plug it is not able, it has not mixed, it is has maintained its identity. So, it has not mixed longitudinally or so. Now, in mixed zone means it has completely mixed, but then there are certain zone which has which is staying for very long time. So, that is basically representative of certain zones inside the TUNDIS, where if the metal gets trapped or the tracer getting trapped, it will be having very large time retaining inside, and it will be coming after a very long time. So, that is basically the dead regions, they are represented by the dead regions inside the TUNDIS. And in that case you will have the calculation of the plug volume, you have calculation of mixed volume, and the rest volume. So, that will be dead volume, and that will be basically we will be calculating it. So, you have the way to calculate, and there are different ways to calculate, and different theta is also considered for that. So, you may define that those particles which are taking more than twice the mean residence time, that you may bring into that category, or sometimes maybe 3 times staying more than the theoretical mean residence time, that may fall into that category of the dead region. So, accordingly we try to define the different type of volume zones inside the TUNDIS based on these analysis. So, you will have we discussed about these plug and the mixed flow which is happening inside the TUNDIS. So, what is meant to be said that these two extremes, that is idealized plug flow or idealized mixed flow, they are the two extremes, but the actual flow will be staying in between these two kind of flows, and so the actual flow needs also to be characterized, and for that you have the different kind of models are developed to characterize basically the actual flow conditions, actual flow which is occurring inside the Tundis, which will be the combination of the plug as well as the mixed flow. So, you have the plug component as well as the mixed component, and based on that we further we try to analyze these reactor or the vessel and judge its effectiveness, how well it is going to be used or to respond to the as a metallurgical reactor, or as a batch reactor or a batch vessel when we are using it in the continuous casting Tundis. So, that we are going to study in our coming lectures. Thank you very much.